starting in chapter 10. So chapter 10 is on series. That's what we're getting started on, the first part of it. So introduction to arithmetic series.
I'm not sure I understand.
Sorry. Okay, so counting on college. When Angela turned 18, her uncle Zachary explained to her that he had been saving money for her college education since she was born. He told her that when she was 1 month old, he had put $50 into a safe deposit box, and the month following, he had added $53. He continued adding money like this each month, putting in $3 more than he had the previous month. The money that he had saved would now pay for Angela to attend any college of her choosing. So we want to write out the amounts of the deposit for the first few months as an arithmetic sequence. How much was added to Angela's college fund in the 12th month? And then we want to write a formula for the arithmetic sequence that determines the amount deposited in the nth month. Check that when n equals 1, representing the first month, your formula gives you 50. And then determine the final deposit on the last month of the 18th year. So first of all, I'm going to set this up as a table. So month and then money. Oh, let it load, sorry. So month 1, it tells us, was $50. Month 2 was 53. 3, 4, ... We want to know how much was deposited on the 12th month. So a couple of things here to remember. This is just to kind of remind you, going way back. A sequence is an ordered list. That's from Math 1. And then an arithmetic sequence is when you add a constant. So that's what's going on here. It's like an arithmetic sequence. And then the other thing about sequences is sequence notation. Is T of n. So we don't use f of x for sequences because it's not a function. We don't have anything in between. In between month 1 and 2, we're never going to have $51.50. We're never going to have 50.5. It's 50, then we jump to 53, and it says we're adding a constant. It's 56, then it's 59, and so on. And our goal is to figure out what it is in the 12th month. So you have a couple of different options. We could fill in the table 5, 6, 7, 8, 9, 10, 11, 12, or we can write an equation, which is what part B wants us to do. So our equation here, I'm going to kind of skip to B and then come back to do part A, is T of n equals 3n plus, what would we want to add here? And you guys can type it in the chat. What would our starting value be? Yeah, and a few people, there's a couple more answers coming in. So this is going to be 47. Because remember, it's not 50 because we want this to be the 0th term or our y-intercept essentially. So that's why it's 47. We'd have to work backwards to month 0. And that's where the 47 comes from. And it says to check to make sure when you plug in 1, 3 times 1 is 3 plus 47, we want to get 50. So then for the 12th month, we do t of 12 would equal 3 times 12 plus 47. We're going to get $83. Do we have any questions on that one? So 10-2 part A says that Uncle Zachary wrote his equation like this. T of n equals 3 times n minus 1 plus 50. And that's what's given to you in the book. Verify that this is equivalent to the equation that you wrote. What's the advantage of writing it this way, and what's the advantage of writing it the way we did? So again, this is how Uncle Zachary wrote it. And if we just distribute here, we get 3n minus 3 plus 50, which is 3n plus 47. So it's the same thing. The advantage of writing it the way we wrote it is you don't have to do any distributing. It's just straightforward. This is like y equals mx plus b, which we're familiar with. The advantage of writing it this way is you don't have to work backwards at all to find the 47. The 50 is what we had on the first month. That's why it was n minus 1 the first month. We get rid of it. And that's where we can just leave the 50. So we're using the first term and not the 0th term. That's the difference. So for part B, it says determine the amount of money in Angela's college fund at the time of her first birthday after he made 12 deposits. So what you want to do here, what we're going to do, we want to know, so each month this is how much money he's putting into her account. So we want to figure out how much she's going to have after that first year. So it's going to be 50 from the first month plus 53 the second month plus 56 plus 59 plus, you're going to keep adding until you hit 83. So I'm going to give you a little bit of time. Try to figure out how much money she has in the bank after that first year. So you have to kind of fill in those missing pieces there. So the total amount of money deposited is the sum of an arithmetic sequence where each term in the sequence represents the amount of money added by Uncle Zachary one specific month. When the terms of a sequence are added instead of listed, the result is called a series. When a sequence is arithmetic, meaning each term differs from the previous one by some constant amount, then its corresponding series is called an arithmetic series. The series representing the first year could have been written like this: 50 plus 53 plus 56 plus ... plus 80 plus 83. So knowing that there's a difference between an arithmetic sequence and a series, how can you tell which one to use to represent a given situation? So we have these nested dolls here that can help illustrate the difference between a sequence and a series. So the dolls are special because each doll fills the space inside of the doll of the next larger size. When one placed inside the other, it said they are nested. So it kind of looks like that. When the dolls are nested, their diameters steadily increase. Notice the top half of only the innermost doll is shown. So each of these would have kind of the top half of them, which isn't shown in this picture, so you can see what it looks like. If the smallest doll in the diagram has a diameter of 5 centimeters and each doll has a diameter that is 1 centimeter larger, write a sequence that represents the diameters from shortest to largest. So there was still kind of a lot there. So here, the most important thing to take away from this problem is what a series is. It's when the terms of a sequence are added together. So this right here is a series because we added all of them. Up here where we just listed them, that was a sequence. So for part A, going back to the doll problem, it says the smallest doll has a diameter of 5, and each doll has a diameter that is 1 centimeter larger than the next smallest doll. Write a sequence. So remember, a sequence is an ordered list. So the first one is 5, and then it's 1 centimeter larger. So the next one would just be 6, 7, 8, 9, and 10. Because there are 6 dolls in this problem. So the first doll is 5 centimeters, 6, 7, 8, 9, 10 centimeters for the largest doll. So for part B, it says, in what situation might you want to calculate the sum of all of the diameters? Then write the series and calculate the sum. So in this situation, for like these dolls, I don't know, you might, if you kind of put them all next to each other and you wanted to see how much space they took up on a table, that might be one reason. But the series here would be 5 plus 6 plus 7 plus 8 plus 9 plus 10. And we would add them. So go ahead and add those really quickly. So A again was a sequence because it's listed, and B is a series because we are adding them. So we get we should get 45 here. Part C is the same idea. It says sometimes they have as many as 20 dolls. So this next one, they give us the sequence T of n equals 3n plus 5. And if all 20 dolls are arranged in a line with each doll touching the one next to it, how long would the line of dolls be? Write a series, so remember series is adding them, to represent this problem and calculate the sum. So the first doll would be 8 centimeters wide. Again, if I plug in 1, I'm going to get 8. 5 would be the 0th doll or the 0th term, which doesn't exist. So the next one would be 11 plus 14 plus 17, all the way until we got the 20th doll, which the 20th doll would be 65 centimeters wide. 65, where 65 comes from, is plugging in 20. So this would be the series there. And we would just, again, we'd add 20 and 23 and 26 and 29, 32, and we'd keep going all the way until we got to 65. Are there questions on that so far? Okay. So we were skipping number 4, but I kind of like it because it helps see what's going on in this problem. So I'm going to kind of go over number 4 briefly. I'm not going to do all of it. Because I think it'll help with number 5 go a little bit more quickly. So going back to that last problem, I didn't actually calculate the sum, and we could have. It's just, like I said, tedious to add all of those. So we want to find another way because we typically know there's usually an easier way. So Flo is preparing to run the 100-meter race at her next track meet. Her coach decides to collect data to see how well Flo is accelerating or speeding up at the beginning of the race. The sequence represents approximately how far in meters she travels during each second of the first 6 seconds of a practice race. So the first second, she went 1 meter. The second, she went 3 meters. So after 2 seconds of running, she's gone 4 meters if we added those together. During the third second, she goes 5 meters. During the fourth second, she goes 7 meters, and so on. So if we added all of these, that would represent how far she ran in 6 seconds. During the 6 seconds, she ran 11 meters, but in all 6 seconds, we would add all of those together. So I want to focus on kind of this picture down here. So the idea here with this rectangle, so not a rectangle, I'm sorry, this kind of these stairs, this is what's going on. If we arrange those numbers into those stairs, the first one, she went 1 second, then she went 1 meter, then 3 meters, then 5, then 7, then 9, then 11. So if I'm actually going to show you what I did before, and I'm not going to write it on here. This is what I did when I did this problem before. If we take the second half of the stairs and we turn them and rotate them, they're going to fit there perfectly because it's arithmetic. So each step is growing the same. So by doing that, if I take those second half of the stairs and I move them over here, I now have a 3 by 12 rectangle. So the 3, where the 3 comes from, it was a total of 6 seconds. Well, when I cut it in half and take the second half, it's now only 3 wide. And where the 12 comes from, this first one was 1 tall and the last one was 11 tall. So now it's going to be a rectangle that's 12 tall. So moving that on to problem number 5. So we're not really going to write anything down from number 4. I just wanted to kind of show how we can do that. So we want to calculate the sum of each of these. So they just kind of arrange them in those rectangles here. So this first one, we have 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5, or 5 times 7. So A is just 5 times 7, or 35. B gets a little bit trickier. So we want to use those ideas. So again, it's an arithmetic series. So each of these steps is growing the same amount. So how many steps do we have altogether? How many stairs would there be? I'm going to try to kind of sketch this one. It's actually turning out terrible. I shouldn't have done that. So you can see there's 16 stairs here. If you count them and it stops at 16. So if I were to cut this in half, I would have 8 stairs. So this second half kind of wouldn't be there. And what I would do with this second half is I would turn them and rotate them so they fit up on this first half. So my rectangle would be 8 wide, but how tall would it be? So the first stair here was 4. This last stair, when I turn and rotate it, was 10. So now it would be 14 tall. So for B, it would be 8 times 14. Again, I take the second half of the stairs and I kind of, from 8 on, I would cut those ones off and I would turn and rotate them so they fit up on top of here perfectly to make a rectangle. It would be 8 wide and then 14 tall. So the series has a sum on part B of 112. So what about part C? So you ask yourself, how many stairs are there? Then you cut that in half. So there's 6 stairs. When you cut that in half, you get 3. And then you take the second half, the last 3, and you turn and rotate them. How tall would that be? If the first stair was 228 and the last stair was 48? So it would be 3 times 228 plus 48.
Who's the little baby? You little baby. Who is the little baby? You the little baby. Look. Is he the little baby? Is he him? He's gonna make you laugh. Who's the little baby? Who's the little baby?
So on part C, again, I started part B drawing it, but it was not going very well. So on part C, it's 3 because there were 6 stairs, so we take half of it. That's 3. And then we add the first stair and the last stair together. So 228 plus 48.
Who's the little baby?
276, I think. So 3 times 276, which gives us 828. So see if you can try part D using that same, I'm going to show the book again. Same method. You kind of count the number of stairs and you cut it in half. And then you rotate the second half of the stairs so that they would land on top of each other to figure out how tall your rectangle is. Because instead of stairs, we want to make it a rectangle. So from part D, we know there are 32 stairs. So half of 32 would be 16. And then we would multiply that by 14 plus 20, or 16 times 34. So this is what I wrote on D, 16 times 14 plus 20. Again, 16 was half of 32. The first stair was 14 tall. The last stair was 20 tall. We don't care what each one was in between. We just want to know what they add up to at the end on that problem. And if the stairs were confusing, because it's hard to kind of show you electronically. We're going to kind of say on this next problem, it's the same idea, but we're not drawing it. So how much information is needed to write an arithmetic series and calculate the sum? So not all of these might not be possible. So on part A, it says the first term is 18 and the last term is 72. So T of 1, that first term is 18. The last term is 72.
Yeah.
And the common difference
So, let's go see what your brother's doing.
is 4.5. Common difference, what that means, that's the same as the growth or the slope if we were talking about y equals mx plus b. So we have a couple of options on this problem. They want us to write the series. So the series would look like this. 18 plus 22.5 plus 27, 31.5 plus 36. They don't tell us how many terms they are. They just tell us that the last term is 72. So we would just keep adding. That looks terrible. Until we got to 72. So that's what this series looks like. And they want you to add them all together. So yes, you're adding all of those together. Yes, it's tedious. If you like the idea of the stairs, you could do it that way instead. You could figure out how many steps there are. So you could count these out, or you could have calculated that, which I think we'll do on another problem. But we can add all those. You guys can add all those. Type them all in, write down your sum. For part B, it says you know that there are 6 terms. The last and smallest term is 21 and the sum is 336. What is the series? What is the sum? So T of 6 is 21, and that's the last term. That's the smallest term, so it's going down. And we know that the sum is 336. So on a problem like this, we don't know the first term, nor do we know the common difference. So T of 1 is a question mark, and the common difference is also a question mark. So they gave us 3 things. They gave us the last term. They told us that there are 6 terms and that the sum is 336. So if we think about those stairs, they would look like this, where this last one would be 21 tall. because that's what they told us. And when we add all of these, we would get 336. So if I think about making this into a rectangle, I would take these last three and I would turn and rotate them, and they would fit up here perfectly. Does that make sense how they would fit there? Not the size of the rectangle, but that they should fit there because it's arithmetic. So these stairs are all the same height. The change between each step is the same height. So this whole rectangle that we're looking at here, we would know that the area is 336 because that's the sum of the series. And we know to find area of a rectangle, it's base times height. The base we can see is 3, and the height we don't know. We know that this little guy had from here to here was a height of 21. We don't know the overall height. This part is 21 tall. So 3 times h would be equal to 336. So the base is 3. We don't know the height. We know that top part's 21, but the overall height we don't know. So we find it to be 112. So 112 minus 21 gives us 91. So that's that first term. From here to here has to be 91 because this whole thing is 112. Questions on that part? So this problem, they wanted us to do a couple of things. They wanted us to, they wanted us to find the sum, which they gave us, and they also want us to write out the series. The series is writing out all the terms. So we still have to figure out what all of the terms are. We know that the first term is 91. So this is 91 plus something, 1, 2, 3, 4, 5, and then plus 21. And we're going to get 336. So we need to figure out what those middle 4 terms are, what the height of these stairs are. And they can't just be any numbers because remember the growth has to be constant. So we need to figure out what it's growing by. Sorry. So from 91 to 21, this first stair is 91. This sixth stair is 21, right? This is a height of 91, a height of 21. So kind of for 5 stairs, it went down 70. So, right, 5 stairs had a difference of 70. That's how I should have written that. So if we divide by 5, so 1 stair would be equal to 14. So this is decreasing by 14 every time. That's not the only way to do it. If you were thinking of another way, you can do it using an equation. So if it goes down by 14 every time, this would be 77, 63, 49, 35, and then you would check again. This one is 21. So it's going down by 14. Again, I did that by finding the difference from the first and the sixth stair. So 5 stairs went down 70. So each stair goes down 14. Part C says there are 9 terms, and the last term, so T of 9, would be 18. And that's all they tell us. So this is not enough info. You have to have a little bit more here. We have to either know the growth or the first term so that we can find the growth, or the common difference, they call it here. All right, and then part D, the last one, you know the third term of an 18-term series is 29. The terms are increasing by 10. What is the series? What is the sum? So we know the third term is 18. No, sorry, is 29. There are 18 terms.
You know, Mama better hurry her ass up.
And the common difference is 10.
You know this one.
So something plus something, first term, second term. The third term is 29. And we want to know what this equals at the end. So it tells us that it's growing by 10. So we could easily find the first and second term, right? This one would then be working backwards, 19 and 9. And there are 18 terms. So we want to figure out what that last term would be, and we'd have to find the sum. So if you think about this as an equation for a sequence, it would be T of n equals 10n plus, not plus. So 10 is what it's growing by. And then remember, we would think what the 0th term is, which would be -1. If we went backwards, it would be a -1 because this is the first term. So the 18th term would be 179. So if I plug in 18, 10 times 18 is 180, minus 1, we get 179. So we need to figure out what this adds up to. We could add all 18 terms. You could type into your calculator right now, 9 plus 19 plus 29 plus 39, 49, 59, 69, all the way to 179. And it's not hard. It's just, like I said, tedious. Takes time. It's annoying. If we think about the stairs, we would have 18 stairs. So when we cut it in half to make a rectangle, that tells us our rectangle would be 9 wide. So again, 18 stairs because there are 18 terms. So we cut that in half and now it's 9 wide. And the height of the rectangle would be 9 plus 179 because that's the first stair and that's the last stair. First and last stair. So our rectangle would then be 9 times 188 to find the area, which would give us 1,692 for the sum here. So if you want to keep adding them up and that's easier and makes sense for you, go ahead. But it's tedious, it takes a long time. And then when you have 100 terms, you're not going to want to add 100 terms. So I like this idea of the rectangles, and we'll formalize this more into an equation next week. But again, you take the number of stairs or steps that you have and you cut it in half. Then you cut it in half so that you can rotate it and make a rectangle. So by cutting it in half, you find the base of the rectangle, or in this case, 9. And then the height is the first term plus the last term, because that's how the stairs heights work out. Okay, but that is it on the beginning of chapter 10. So a couple of things before you guys go. Your chapter 9 test is tomorrow during class. If you have questions, I'm happy to stick around right now and answer them for you. Your chapter 9 work, so the CudaWorks assignment, I believe, is due online on CudaWorks at 10 p.m. tonight, the one from yesterday. And then your assignment from Monday and that is, so your notes from Monday and then your closure problems from yesterday, those are both due by 10 a.m. tomorrow. This stuff from chapter 10, that's not due until Monday, so you don't have to worry about it. Yes, some of the homework problems are review from chapter 9, so you may want to do it, but this homework isn't due until Monday. So chapter 9 stuff is due tomorrow. The online part is due tonight to make sure you get that done. And then test tomorrow, chapter 10 stuff due Monday. Questions about that? So if you have any questions, stick around. I'm happy to answer questions from anything from chapter 9 or anything else. Otherwise, you guys are free to go, and I'll see you for your test tomorrow.